Good morning. My name is Osvaldo Vascour. I'm with the Academia Industry Innovation Team, and today I'm going to be talking about the digital plan template for operational insight. This is the third part where we take the data that we have been able to classify and we can apply mass balance or modeling and do that in real time. And also how we can extract the subset of data when the unit is running okay to develop predictive models. So that's what we're going to be talking today. So again, we get a lot of raw data. And we were talking before that you need to transform that data into information. So we add event frame to get that. So then we have information. So the data is form. So it has a shape. And then we can generate insights. And when you get that and you got that insights, we can then train the set data with the data set and analyze and develop models. And this is something that we have been practicing over the last 2 years with very good results. So the first step is to organize the context to the system, add the real-time context so you get data and events. Then you extract the data so you can visualize it and start looking at things. But most importantly, when you got that data classification, you can model. And that modeling enable you to do a lot of additional things. So in this case, this is the hierarchy of how the data is being shaped as you acquired, validated, classified, so you can do some analysis. But if it's good, of course, you can use it for estimation and you can do prediction. If it's not good, you just throw it away. And that's going in time. So you just do it when you can. And then when the unit, we call it happy, you can do things, and then you can coordinate your plan so you can optimize the different areas of the plan and optimize the whole system. So the next step that I was going to say is that I'm going to focus here for a case that we have been working where you want to optimize your yield, the recovery in this case of the metal, in this case copper could be, and that one has a certain shape. So we know that when we are optimizing, we're always looking for an optimum, but you need to find the right size, which sometimes is unmeasured, so you have to generate that with the soft sensor. And the most importantly, the shape of that curve distribution is important. So if you do have an analyzer and you get that, you can develop a shape analyzer, and then you can relate your shape with the recovery so you optimize the speed on how you're running the mill to get the right size so you don't have indigestion in your system. That's a metaphor that I use a lot to explain to people on how this works. But the most important thing is that you need to classify again the data sets. So you have to be in the blue for all these to work. If you are in the orange, you might be able to use it, but you are not 100% sure that that prediction is going to be good. So you classify first, model your soft sensors, and then you optimize and find what are the best operating conditions to get the maximum money, or in this case, the best copper without throwing any copper away in your tails. So the yield calculations. The yield calculations are feasible because we do have usually the tonnage coming in, and then you get these red dots where you have this analyzer. So you have the copper concentration in these three sites, and then you can do a mass balance. So you have this called the three formula equations, and you can calculate your recovery as you can see here. And then if you do the right measurements, you can do that for the scavenger, and also you can do that for this other cleaning and the other separation. So you start using this technology by using these templates, and then you just apply them, get the right data, validate, classify, predict. And that number is predicted from a rigorous mass balance. And then again, this is a rigorous mass balance. You check, as you can see here, is true. Then you can estimate the concentrate flow, the tail flow. And when you have that information, you can plug it for the next section, for the other section. So you start predicting and you have a very good augmented system to do a lot of things that before that was impossible. So this is show you here the way that it looks in PyAF, the elements, and then here you got the concentrate flow estimate, the recovery estimate, your tail from based upon the C measurement that you have from the X-ray analyzer. And this is only going to be calculated when you are with the unit running okay. So the next thing that we are going to show you very quickly here is that you can have now the particle size. So this is where you have a sensor and we're predicting it. And how we obtained that one was by collecting that data, uh, getting the data in the running mode, extracting the particle size and the 5 variables which are usually associated with that, which are the cyclone pressure, the process feed rate to the cyclone, and the two waters and the energy, and then you end up with these linear regressions, which are very good. And then you just plug this number back in into the template that I'm going to show you in a minute. And you can run different type of neural networks, or you can use other type of algorithm if you want to test if you are going to improve from the basics. But I have found that this is very good and very reasonable. So this is how it looks when you plug in the coefficients, and then you know these variables, which are your operating variables, and then you get your output results. So this is how it looks in your attributes when you are doing. And the analysis, of course, is just a multilinear regression equation or whatever equation that you have found. It could be nonlinear, it could be exponential, it could be very complicated, but then you just put it there in the analysis, and I'm going to show you that in a minute. So this is how it looks in the estimate. Here you put the first term, the second term. You can have up to 10 terms if you want it. They can be a lot more complicated than I want to have here. But at the end of the day, you have a bias, and that's you adjust it, and then you have the output, and you can clamp the output if you want to make sure that it's within reasonable bounds. So that's there. This is another one in where you have a lot of measurements of the sizes for the different um, areas. So you can have this linear regression, and then you can estimate the shape of your size distribution by um, having this distribution put here. And I'm going to show you how that works. So you have the shape, which we call the distribution module, and the top measurement that is here, the intercept with the largest size that you can have available in your system. So this is how it looks, the results in PyF. You have the two sizes, the shapes that are calculated at the beginning of the when you are starting to eat and when you are finishing eating. You got all the combinations, so you have the beginning of your food till the end, and then you get the maximum recovery because you are optimizing your shape and your size distribution as you go through. This is the equation that takes all that data and does the linear regression estimator, and I calculate these two data points, which are extremely valuable to model your flotation. Then again, this is the way that it looks. And then again, we are here, and you can use some other models, as you can see here, which is I'm going to show you that very quickly. So let's go into the practical, showing the practicalities of this system here. Now we go into our show you here. So what I'm showing you here is basically what I was showing you. Again, this is the running in right now PyF, and that this is in the elements. And now the elements, the quality area of the template is always very particular, because in this case, because I'm in the grinding area, and you can apply in more modeling into it, as we're going to show you. The basic modeling of this grinding area is that you got the size distribution, as you can see here, and you can calculate that environment here. So by having that information, you go into your analysis, and the first thing that you can do here is to do your simple mass balance of the amount of material coming in divided by the amount of material coming in plus all the water. That give you the percent solids on your overflow. This number is very important because that's kind of the quality parameter that goes into your flotation, which is your next uh, vessel. So that can be calculated, and you can adjust it as you go with your experience. The next thing that I was going to show you here was this flotation estimate that we talked briefly. So this is how they look. Now you get the data, you validate your X-ray analysis, and then you can calculate your concentrate flow, the metal recovery, and the tail flow. By having that number, then you can relate it to your grinding and relate it to many of the other operating conditions that you're running, so you can optimize or find out what are the key elements that I need to optimize. The next thing that I wanted to show you was the other one that is doing the calculation in real time. No, this modulo. So this is how I already show you that. Basically, this is just running in real time, and you can calculate, and it give you again the side module, which is 192, and the distribution module, which is 0.39, which is a pretty good number. And then if you want to do flotation, it's going to be zero point 0.7, 0.75 maximum, but that's basically that is a very nice sharp distribution. So all the bubbles are going to be attached and you got a brilliant flotation. So those are the things that we have been finding. Now you can extract that data as we were talking about, and I'm going to go here, see if this is still running. No, that's not running in this environment. So I got it running on my other system. That this is what I was going to show you was my Studio AssureML, where I have a set of data, as you can see here, and I'm going to open it up. And as you can see here, we can test the neural network, we can test the linear regression or the decision forest tree. All that data becomes available in this thing. When I click here, you're going to see the variables that becomes available, and you can launch the selector of the variables. And here I have the whole mill available, and this was data extracted from data link. So you can select which are the key variables that you want to do, in this case, to maximize your calculate your recovery or calculate your grade, anything that you want to estimate based upon your operating condition that you have available. And then we go into selecting your model. So here you select, I want to get the rougher flotation concentrate, which is the grade, and then you find out what that could be. And then you run your model here. It will take a minute or two, and you end up with the parameters which are associated with the model. And then bingo, you ended up with the variables that are going to enable you to see. You see, you got here the set of variables that you're going to go back into your environment, excuse me, here into your environment, and then you just put those into this environment, and you put the, the variables, the coefficient. You just type the coefficient, and then you put the variable that you selected, and then you start predicting your recovery, your grade, whatever you want to predict. It becomes running very well. And this has been very nice, because people can learn a lot. They know what's important, what's not important. And if you have any questions, just let us know, because what we are really doing here is to show you that once you get that going, you can really have a good assessment of a mill completely with the key variables which are predicted. And you see this recovery is predicted, this recovery lead is predicted, and then you know what are the things that you need to do to optimize the metal recovery based upon the conditions that you're operating. This is another thing, is that when you got this model the way that is defined here, everything becomes automatically. You just click on the variables, and then those tables are generated automatically from the PyF. So PyVision becomes extremely powerful, and there are many other things that we can do here. We got another one where we have put together again for another circuit. We got the particle size estimate, we get the metallurgical calculation, and also we got this estimation of the hole depths of the air hole depth, which are based upon these other variables. So you have those predictors. By having these other predictors, and the key variables for the grinding, you start optimizing, in this case, your lead and your zinc. So that's basically what we have done, is that we have taken this four-step process where we organize the data, we get the events, we classify the data, we extract the data, then we model the data, and then we start tweaking what are the best opportunities to optimize the recovery of your metal with the minimum amount of water consumption and the minimum amount of energy consumption. So that's what we are doing. We are trying to maximize yield, reducing the operating cost. Well, thank you very much. And if you have any questions, let us know.